Using everything we've learned in this unit, we can calculate the pH at different points during a titration. But before we do that, let's review how to calculate the pH of acids and bases. Strong acids and bases react 100%, so we use moles and stoichiometry to figure out how much H plus or OH minus there is, and then we can find the pH. Weak acids and bases are at equilibrium, so we can do icebox to figure out how much H plus or OH minus there is, and then find the pH. Salts and buffers are examples of weak acid-base systems, so we can do icebox, although for buffers, the Henderson-Hasselbalch equation is faster. In the example problem, 20 ml of 0.1 molar HCN is titrated with 0.1 molar KOH. So we're starting with the weak acid, HCN, in the beaker, and the strong base, KOH, in the burette. Our goal is to figure out what the pH is at different points during the titration. Let's start by writing out the balanced equation. HCN is an acid, so it donates H plus to KOH to make water and the ionic compound, or salt, KCN. The pH curve should look something like this. It starts at a lower pH because we're starting with the acid in the beaker, and it goes up to a higher pH as we add the base to it. Since we're starting with 20 ml of HCN, and we know the concentration of HCN and KOH are both 0.1, that means it should take the same amount of KOH to neutralize the reaction. The equivalence point is the point where we have the exact amount of acid and base for the reaction to be neutralized. So in this example, the equivalence point is 20 ml of KOH added. Let's start by finding the pH in the beaker at 0 ml of KOH added. At this point, none of the base has been added yet, so there's only the weak acid solution in the beaker. Since we only have the weak acid, we'll do an icebox to find the pH. Write out the equation for the weak acid reacting with the water in the solution. HCN donates H plus to H2O to make H3O plus and the conjugate base. Start with the initial concentration of the weak acid and 0 for the products. Use X in the change row, and consider the change amount, or X, negligible when you're already starting out with the initial amount. Use the equilibrium expression to solve for X, which will give you the concentration of H3O plus. Then use the concentration of H3O plus to find the pH. At 5 ml of KOH added, the strong base will react with the weak acid that's in the beaker. Let's start by writing out the equation for the acid and base reacting together. At this point, only a small amount of base has been added. It's less than the equivalence point, so it's not enough to completely neutralize the reaction. This is called a partial neutralization. The strong base will be completely used up, some weak acid will be left over, and its conjugate base will be made. A weak acid and its conjugate base together is called a buffer. So just like we did with other buffers, we'll use a mole box to find the pH. Calculate the moles of HCN and KOH, so multiply their volume by their concentration to get the moles. The strong base will be completely used up, so use that amount for the change. Again, since the strong base is used up, only the weak acid and its conjugate base are left in the beaker, which is a buffer. And that means we can use the Henderson-Hasselbalch equation to calculate the pH. At 10 ml of KOH added, we're still not at the equivalence point yet. Remember, the equivalence point is 20 ml of KOH added, so 10 ml is the half equivalence point. At the half equivalence point, we should see equal amounts of the weak acid and the salt product in the beaker. Write out the equation for the acid and base reaction. Use a mole box and calculate the moles of HCN and KOH. The HCN in the beaker doesn't change, but you'll need to calculate the moles of 10 mils of KOH added instead of just 5. Use the entire amount of KOH for the change since it gets used up. And notice that at the half equivalence point, we now have equal amounts of the weak acid and its conjugate base. So we still have a buffer, which means we can still use the Henderson-Hasselbalch equation to calculate the pH. The half equivalence point is the point when the moles of the acid and the moles of the conjugate base are equal. So the concentration of the base over the concentration of the acid is 1, and the log of 1 is 0. That means the pH equals the pKa. So at the half equivalence point, the pH equals the pKa. At 20 mils of KOH added, we've reached the equivalence point, so we know the acid and base should react completely, and we should only be left with the products in the beaker. Write out the equation, use a mole box, calculate the moles of HCN and KOH, subtract the entire amount of KOH because it gets used up completely, and notice that the entire amount of HCN is also completely used up. This is how we know we're at the equivalence point. There's exactly enough acid and base to react together, so the only things left in the beaker are the products, which are salt and water. Now, how do we determine the pH of a salt solution? Dissociate the ions, cross out the spectator ion, and write an equation with the remaining ion reacting with water. CN- is weak, so we'll need to use icebox. An icebox uses concentrations, so divide the moles of CN- by the volume of the solution. But be careful, make sure you use the total volume of the solution, which at this point is the 20 mils of HCN plus the 20 mils of KOH added together, for a total of 40 mils, or 0.04 liters. Now use the equilibrium expression to calculate the concentration of OH- and find the pH. But we'll need to use Kb since the OH- in the products makes the solution basic. So calculate Kb first, then calculate the concentration of OH-, and then find the pH. At 25 mils of KOH added, we're past the equivalence point. So we know the acid is completely used up, the salt product is made, and there's some excess strong base added in as well. Write out the equation, use a mole box, calculate the moles of HCN and KOH, but this time HCN is used up first, so use the moles of HCN in the change row. And we're left with KOH and the salt product in the beaker. The weak base in the salt contributes very little to the pH compared with the strong base, so we're going to ignore it. The strong base will dissociate completely, so all of the KOH will turn into OH-. Calculate the concentration of OH-, so divide the moles by the total volume of the solution, which at this point is 45 mils, or 0.05 liters. Then use the concentration of OH- to find the pH. Let's review how we found the pH at different points during the titration. At 0 mils of KOH added, there's only weak acid in the beaker, so we used icebox to find the pH. As the strong base is added to the weak acid, a partial neutralization reaction occurs, creating a buffer, so we used a mole box to find the pH. At the half equivalence point, the weak acid and the conjugate base are equal, so the pH equals the pKa. At the equivalence point, all of the reactants are used up, and there's only salt left in the beaker, so we used an icebox to find the pH. And past the equivalence point, there's salt and excess strong base in the beaker. But the salt contributes very little to the pH, so we only use the strong base to find the pH.